would like to know, first of all, why do we need verification IPs when we have different verification environments available within the company, within different groups. So, I mean, what makes it essential to have a VIP which would, I mean, you buy it at a certain cost and, you know, pay for it extra. So the basic reasons are, first of all, there would be a reduction in time to market because you already have a ready to integrate model that you can use for your verification. So it accelerates your development cycle. And then the second would be the quality, because we have, I mean, would have spent quite a lot of time developing the verification IP, and it would have been tested with various customers. So all the, I mean, it will have all the coverage points defined, all the assertions in it, and it would be compliant to the protocol. And because it has been used with multiple customers, it would be fair to assume that it is, I mean, it's quite capable to find bugs in a design which is being developed in-house. So thirdly, it would be basically reducing the costs of the company which would be buying the verification IPs, because you won't have to spend a lot of resources trying to, I mean, deviate exactly from verifying a design and, you know, start focusing on writing a verification IP to develop it. So if we get that verification IP from a, I mean, from a third-party vendor, from somebody who's specializing in making a verification IP, that would be of a very little cost compared to developing that verification IP in-house. So, I mean, you can reuse it vertically as in a SOC level as well as at block level, and in terms of like you can have a horizontal use for it. You'll be having multiple chips with a similar protocols in it, so that same VIP can be used across multiple chips. So, I mean, ultimately it would be cheaper for you to buy that VIP from an external vendor instead of trying to spend your man-hours and a lot of resources on trying to build it yourself. So, I mean, essentially we think that it would be costing a VIP less if you, I mean, if you get it ready-made from a person who's from a company, from a vendor who's specializing in developing those VIPs rather than developing it ourselves. Okay, so next is basically benefits of using a system Verilog based OVM or a UVM verification IP. And I mean, nowadays it's basically everyone, all the people are wanting to have a verification IP which is reusable and which is very flexible in terms of usage, supports multiple languages and multiple simulators. So if we have a OVM compliant verification IP, it provides all the following requirements, like we have for easier integration, which reduces the number of bugs when we integrate it into a multiple SOC platform. I mean, it's highly flexible, can be used both at a chip level and a block level, and it's highly configurable, so that can be used with different chips which use selective features or a particular interface for a particular protocol. And then it reduces the development time for newer VIPs. So if you build something on top of it or for a similar protocol, let's say that, I mean, we have something from I2C, so to build a VIP for SPI or a UART would take a considerably lesser time. And then it's always wiser that you have a multiple language support, so that various languages like E, System C, C, System Verilog, all those can be combined in a single top-level verification environment, and I mean the environment can run as such without having to make all the verification IPs in the same language. So some more benefits we can have. I mean we say that for system Verilog VIPs we'll be having is the HDLs as such are not very friendly for verification. So they do not support object-oriented programming. They don't have a considerable randomization, and functional coverage is a prime feature that is lacking there. So for a system Verilog based VIP, all of these things are highly highly programmable, or let's say we can change them as we want. So you can add as many constraints, you can add functional coverage, you can add as many assertions you want. So there's no separate language needed to do different things. And then with the system Verilog, we have we have support for multiple. Most of the simulators are now supporting system Verilog, so it should not be a issue with like getting syntax errors or getting different. A language which is supported only by one particular vendor. So let's go ahead with the steps that are needed for developing a verification IP. Here, what is preferable is defining a generic component. So generic components would be like a sequence item, a driver, monitor. So why do we call it generic? Is because let's say for similar protocols, like for a communication family like I2C, I2S, UART, GPIO and SPI. So for these protocols, they have similar sort of interface. So for all of them, if we define a basic component, then we can we define for one component and we can reuse them for all the different components. So it's basically you define them once and it can be reused in multiple protocols. So an example is basically defining a sequence item for SPI that can be reused for I2C. So we define a class which would basically have a TX and RX components, TX and RX bits. So as we see here, it can be used for an SPI protocol. So we can drive the data as we want. And similarly for I2C, the same class can be extended, and we can drive a different set of values in a different fashion on those ports. Then if we talk about reusability, so developing reusable sequences is of prime importance because we want to reuse whatever we have done for block level verification at an SOC level too. So whatever sequences we write, they should be able, they should have enough controllability and randomization to be used in case of, when we use them with the virtual sequences too. So let's say we define a read sequence and a write sequence, and then we can randomize it at a top level to basically create different scenarios and different error scenarios. So this example illustrates this sequence reuse. So let's say that we defined certain sequences for write command, read command, and then read after write, or write after read, and then various different long commands, long write and long read commands. So once we define all these commands at a top level, we can say that I want to randomly select any of these commands, randomly out of for n number of times, and then we can just do that sequence. So it's highly, it's like very comfortable to test different scenarios in a different sequence in a totally randomized fashion. And yeah, this part is too important. When we say that we should have an agile approach to new VIP development. So this means basically that we'll be phasing out the deliveries. So whenever the customer is ready for testing the DOT, he doesn't need to wait for a complete verification IP to be delivered. Instead, it would be like, basic read and write would be working first. So that can be started. Customer can start to verify the DOT at that point itself. and later on in a phased delivery we can have different features developed. So gradually, as and when those features are developed, as we see in this diagram, so gradually, let's say initially some basic sequences are there, then we will be having scoreboards and more complex sequences. Then we can add protocol coverage and protocol checkers and coverage to it. Then we can talk about migrating OVC or UVC into eTest benches. So this is required because nowadays customers will have multiple verification IPs in different languages. So it can be a requirement of some customers that we want to have a top level environment in SpecMan, in E or SpecMan, or in system Verilog OVM. So we can provide basically a framework in which there would be a wrapper, E-wrapper around the system Verilog VIP, and then that E-wrapper can be integrated into a top level environment so that the entire environment works with E sequences now. Similarly, we can have a SV wrapper on top of a EVC. So in that case, we'll be having a system Verilog verification environment, which can be, which will internally can have various EVCs, e-verification IPs. Then we can have like basically how to develop the bus monitors. So it would be basically building sequences for reconstructing the received frame or the data into sequence items. So whenever we receive the data, would be collecting the data, framing them into a particular packet, and that packet can be given to different layers, let's say for coverage, for protocol checking, and for scoreboard. So this basically defines this section of code defines that different methods we can have. On the left side we have a monitor code which would in which we used to like call different methods on a particular item. But if we define it in terms of sequence, we can have different functions like update RNW and update ACK. These functions can be called directly as a sequence item dot update that particular method, and then we can easily pass on that packet to the scoreboard or wherever it needs to be used. Similarly, here it is shown that for that particular, let's say we define a coverage item, FB descriptor, or an address. So we'll be defining all the coverage points, and then those coverage points can directly be used for inside the monitor code we can just call when we say that we want to sample them. So when we sample it, all those coverage items would be covered automatically. So we don't need to specify, we don't need to stress on defining these coverage items in different places. We can have all of them in a single monitor code, export them through a packet, and it will be very easy to use them in monitor or in the scoreboard. But yes, one thing that we need to take care of is because certain simulators, they don't support the definition of coverage point to be made after it is being used. Let's say it's common in E to define the order of definition is not important, but with some simulators we found that let's say for Aldec and monitor, if we define a cover point later than using it in a cross definition, we got certain issues. So it would be advisable if we define them first and then use them in a cross coverage points. So overall, in a summarized way, we can say that the increased use of VIPs for complex verification environments would be very beneficial. It would reduce a lot of time, and it would improve quality a lot. And so we will be using use of methodologies like OVM and UVM for multi-language support. Again, would be very helpful, and it can help you in having multiple languages and just create a wrapper on top of it and use it in use all of the different languages in a single environment. Thirdly, creating generic components that can be reused would be very helpful, because you can have multiple protocols use those generic components, the similar protocols. Yeah, prioritized based on customer requirements. So as and when a particular feature is required, so that can be prioritized based upon the customer's need. And again, the last point is agile based delivery methodology. So it would be a phased out delivery so that customers can start the verification as soon as they get the VIP, and then gradually we can implement multiple features in it, so that at least the DUT verification doesn't suffer, and gradually the quality would be improved. So with that, I would I come to an end of it, and we can have questions.
There's one question online. Yeah. I can answer that. BFM is the best functional model. There's one question here from Martin Abrams of Jasper.
Yes.
Lampard, sorry. Martin Lampard of Jasper. Sorry. So the question from Martin Lampard of Jasper is more general. Is how many people actually use Agile development methods in their verification? And I know we do in TVS when we're developing VIP. And we can do phased requirements delivery to customers. There's probably I would say probably about 10 companies in the room, 10 different companies in the room, and no one's putting their hand up. Is there anybody online want us to talk about agile development for verification?
Yeah. Yes. So the benefit it gives is mostly in the cases in which the DOT is still under development. So when we say that only a certain part of DOT is ready, so that only that particular feature is required at that point of time. So even in that stage, if the verification IP, if we are waiting for complete verification IP to be delivered, so that would be very late in that case. So whenever that verification IP is being developed, the verification team can develop that particular feature and start testing it with the design team. So it's going to be beneficial for both the verification team as well as the design team. And when they get the bandwidth, the verification team can support additional features that have still not been implemented in the DUT.
Okay, there's one other online question, which is why is UVM a coverage-driven verification methodology? I guess the answer there is it doesn't need to be, but most people use it as a coverage-driven methodology in the way that SpecMan and E doesn't need to be coverage-driven, but most people use it that way as a way of understanding what verification you've performed. Doesn't look as though there's any more questions, so I think just to finish off, we're going to hand back to Bristol and hand over to Steve Holloway from Dialogue. So thank you to Manish.